Actually, very on. Careful. Good morning, everyone. Welcome to routing in Prague, IETF 118. We've got busy agenda, so not well. Hopefully by now you are all familiar with the document. Please read it and reread it. Any contributions to IETF are subject to IETF rules. IPR disclosure, RTGWG applies policy. We ask for IPR during document adoption into working group and working group last call, and unless every author, co-authors, contributor has responded, document wouldn't progress. Status, BGP peak is in all, it's cut, right? Yeah. So BGP peak is almost done. TILFA, we've got very interesting discussion directly after chairs are done. So good progress, good discussion as well. We've done early review for SRv6 egress protection, and we are looking for a shepherd, so please do volunteer if you find this interesting. QS model is going through pre-working group last call reviews. So now with young doctors and other directorates on its way to working group last call. VRRP document is pending IPR disclosure. So IPR disclosure is about 30 years old, and we talked to EC. There are some complexities in getting it. Probably we'll try to work around the process and just proceed with it. So agenda for today, we're going to it. And thanks everyone for being here remotely and locally. And we'll start with Stuart. Stuart, are you there?
I'm here. Hang on, I'm here. So can I have, I think I've sent you my slides, haven't I? Right, thank you. So we go to the straight to the next slide. I'm going to talk about the TILFA draft. Next slide, please. Right, so the TILFA draft underwent a series of area reviews prior to being sent to the IESG. In particular, Guyan Mishra's ops review pointed out that it was unsafe to deploy TILFA without a loop convergence strategy also being deployed. On the list, there's a trivial pathological topology presented by Guyan, and another one was also entered into the discussion. And we have observations of deployed networks that noted that microloops do form unless a microloop strategy is deployed. Now, in my view, there is no point in having an emergency repair mechanism if it immediately gets damaged by microloops that form within a few milliseconds after you start convergence. So next slide, please. Next slide.
Stuart, you have control of the slides. Can you try?
I do it here. Okay, sorry. I should have practiced with this. Thank you. Right, so we now need to consider draft Bashandi, which is the companion microloop draft. This draft has not progressed well and arguably is not well developed. I think it needs review and it needs development with an operational focus. So, for example, I note that there's no sort of decent guidance about how you have a synchronized view on how long you should remain each of the convergence states. I think there is a strong case that this draft or another approach needs to be incorporated in or co-published with the routing TILFA draft, because you do need some guidance to people who are going to deploy TILFA on how to do loop prevention. Next, I'll do it. So I have a few observations here. Given that we have emerging evidence that TILFA is operationally unsafe without a microloop strategy, and noting that the post-convergence congruence was originally to avoid microloops, and noting that ingress packets may not actually reach the PLR post-convergence, we have to ask whether the post-convergent constraint should be required or simply optional. I note that removing the constraint would not result in any incompatibility with deployed TILFA implementations. And I note that choosing another microloop strategy would likely not be incompatible with pre-standards draft Bashandi implementations. So, after years of almost silence on this work, there has recently been considered discussion of the TILFA work on the routing area working group list. I believe the chairs are considering the best way to move this forward, and I think it needs to be driven by the chairs rather than the shepherd, unfortunately. And I would suggest we need some form of virtual interim meeting to focus on the issues and ensure that when we publish this, we publish a complete viable specification for people to implement. And that concludes my remarks. No comments? Okay, over back to the chairs.
So Ahmed, you're the first in the queue.
Okay.
Can you guys hear me? I was supposed to come in person, but due to family issues, I had to actually cancel my attendance. But a couple of important comments. First of all, this is not the first time we attempt to address fast reroute. I mean, Stewart himself co-authored 2 RFCs, and I really don't see why there is a reason to combine microloop avoidance and TILFA, which has not been done before, and I really don't see how TILFA makes microloop any worse or better. Actually, it makes it better, but any worse than what it exists right now. I would just think that we follow what Stewart did, and we have a separate draft for microloop avoidance. The same thing happened with the 2 RFCs that Stewart co-authors, and I believe the other co-authors have made the same comment, and there was wording that has been suggested, and I will adopt this wording and we close this issue. But trying to basically push microloop avoidance down the throat of FRR is not really the right approach, in my opinion. Thank you very much.
So may I disagree with that? When we first did the work, I mean, I started this work 20 years ago, right? When we first did this, then when we first did fast reroute, we weren't sure how we were going to do the microloop convergence control, but we did notice almost immediately that we needed it. I think the world has moved on in that 20 years, and I don't think we should be advising anyone to deploy a fast reroute strategy without co-deploying a microloop avoidance strategy, because we know that without the microloop avoidance strategy, you destroy the fast reroute parameters during the convergence process.
I tend to disagree, Stuart, because this solution is already deployed for many years in many places. And when you say advise people to deploy, you're actually saying something that's actually quite late. It's already deployed, it's already working. So that claim that is worse or makes things worse is really not corroborated. If you think so, please go ahead and propose a draft that combines both and let it go to the working group discussion. But I don't think what you're saying is correct, in my opinion.
Well, we've had two operators comment on that.
Bruno.
Bruno de Crane, Orange. Thank you, Stewart, for your comments. Can you go back to slide 4, please? So
Yep.
I have a lot of comments actually, but the first one is I fully agree with Ahmed. We have two different problems. One is fast reboot, which is local to the router and completely independent from the IGP. And then we have the IGP convergence, which is creating the microloops. It's not TILFA or fast reboot, which is creating the microloops. It's IGP convergence. So it's a different problem. It's two different problems: fast reboot, local, and then the IGP convergence, which unfortunately create microloops. And I fully agree we need two solutions. I agree we need both to be implemented, and obviously both to be specified. I just really don't understand why you want to mix both problems in the same document, or we never did it.
Because
We never did it. You have written a remote LFA, which has exactly the same problem or non-problem, and you didn't mix it with microloop. So why now you want to mix both?
well, in the TILFA draft, it does point to draft Bashandi as the preferred microloop avoidance strategy.
So do you want that to be removed?
I think there needs to be some text in there that makes it quite clear to the reader that this is essentially not going to give them what they think they're going to get unless they have some guidance to determine how the network is unconditionally safe without a microloop strategy, or they deploy a microloop strategy. I don't think the former is really possible, because if you take one repair or a pre-existing failure not repaired or a maintenance operation, then you can't be sure that the network is still microloop safe. So I think you really have to put strong words in there to say that you must take microloop avoidance precautions in deploying this. Otherwise, you get microloops and there's no point in deploying it.
No, I disagree. There is point in solving fast route. There is also point in solving microloops, but it's two different problems. So regarding your comment, we have text about microloops. We discussed, thanks to Sasha, and we proposed text. I thought we had agreement on the text to add. Do you now disagree with the text, or?
I think I would like to see the document in its entirety. I don't think you've published an updated version of the document.
No, but we send the text on the list to agree on the text before putting in the document. And I think Ahmed said he will insert that text.
I think I would like to see the document as a whole, because I think what you've got to do is you've got to see what, and this is where Guyan's review sort of came in. You've got to take a holistic approach as to, if someone reads this, what will they do? And I think it needs to be much clearer that the importance of the microloop strategy.
Much clearer than the text we agreed?
I think I would need to reread the text.
Okay. I thought we agreed with Sasha and you that the text was good, but we can rediscuss it. But we need at some points to have all comments and to close the comments and work on the solution, because we already had a specific meetings with you in London, which is quite a few months ago.
Right.
I thought we had addressed all your comments, and then you have blocking.
So you had addressed all my comments until I realized just how trivial the topologies that would cause microloops were, because it had always been asserted with this draft that there was no issue, and it had always kind of been put under the brush to one side what would happen to the traffic trying to get to the PLR. There was really very little discussion of that. There was always a focus on post-convergence congruence being the method by which you avoided microloops. And when it becomes obvious just how trivially the system gets broken, for example, this system can't work in a ring network.
We all agree as Stewart on that.
Yes.
So there are microloops, and we want to solve that.
Right.
So please be specific on your comments, and we'll address them. But we can't have we can't wait for forever for new comments. And
I was all happy with this until, as I say, until it came home to me just how important the microloop problem was, and that came up as that was triggered by the ops review.
you're very aware of microloops, so I'm surprised
Yeah,
you discovered it lately.
Gentlemen, at this point, I think both points are well made and well taken. We've got more people in the queue.
Can I comment on slide 4?
Please do.
So I disagree with many points. You say it's unsafe to deploy TLFA without microloop strategy. So microloops is not created by TLFA. So essentially, you say it's unsafe to deploy link state IGP without loop strategy. Well, we have 20 years of experience deploying link state IGP, fast reroute solution, LFA, remote LFA, TI LFA. I completely disagree that it is unsafe, and I completely disagree that it is caused by TLFA. In terms of constraint on post-convergence path, I'm not sure you're reflecting the status of the working group. I think many people want the post-convergence path for many reasons. You can read section 2. It is described why we want the post-convergence path. I'm quite surprised that your summary of as Shepherd is that we don't want the post-convergence path anymore.
But I'm also
is it your
acutely
personal opinion, or it is the Shepherd summary?
So I'm aware of comments of people worrying about the size of the label stack that's needed to be pushed. I've heard many comments about the number of labels it takes to be congruent with the post-convergence path.
For link failure in a network with symmetric links, it's guaranteed to be less than 2.
Indeed.
Any implementation, even the less capable ones, can do that.
Indeed. But that doesn't come through in various discussions. Anyway, so I do admit that I have personal concerns about this, and as far as I'm concerned, that's not a reason to block the draft. But I do think we need to consider whether we need to provide more liberal guidance to implementers about how they calculate the repair path.
Okay, so in summary, please be specific in your comments. Let's not mix your personal concern with the Shepherd work.
Sure.
Sasha, please be quick. Sasha, you there? Peter.
Peter Pshenak, Cisco. Hi, Stuart. So I tend to agree here with Bruno. TLFA as such doesn't cause microloop. Microloop is caused by the post-convergence, switching to post-convergence paths. As soon as you are on a TLFA path, you're fine. So we should not make any conditions for TLFA to progress on any microloop documents. We can say in a topology where you use TLFA, if you switch to a post-convergence path, there is a likelihood that you make for a microloop and you can use any techniques. Can be you can just be on a backup path for a longer time or so. There are many other techniques other than the one described in the microloop avoidance draft. So I would really keep these two things separate.
Okay, so I think probably what we're coming to is we need an operations section in the draft, don't we, that provides the guidance to someone deploying this about what the limitations are and how they should address those limitations through a microloop conversion strategy. And we probably, by the sound of it, should note that any of the microloop avoidance strategies are permitted. And not specifically focus on the Bashandi draft, which is directly referenced in the document.
Exactly. We should say there are microloop avoidance techniques. We can give examples, but we should not go into the details how to solve the microloop because it's a different problem.
Oh, yeah. So, right. So let's try and get an operations section in there so that the operators are aware of what they need to do.
Yeah, thanks.
Thanks everyone for the comment. So my preliminary assessment, and we really don't want to make progress of TLFA draft contingent to progress of microloop. So I suggest Shepard and other team to work on text that would satisfy Stuart as Shepard, as well as working group, and that would be the way to progress. Stuart?
Right. And we got a side meeting on Wednesday. Wednesday, isn't it?
Yeah, we are trying to set up a side meeting on this topic. So far, we are targeting Wednesday. Once we have the time set decided, I will send an email to the list. Everybody is welcome to join the discussion.
Thank you.
But practically, I think we kind of understand where it should go, given the discussion and sentiment in the room. So we'll discuss it further. Thanks, Stuart. Thanks, everyone.
Thank you for your time. Thank you.
Can I say a few words?
Sasha, we
Okay.
close this discussion.
Okay.
Please do join the actually side meeting. It's not going to be.
I just hope we will hold this interim meeting mentioned by Stuart, where we will be at least less restricted by time. Thanks.
Thank you. Linda?
Good morning. Today I'm going to give a brief update to the changes to the multi-segment SD-WAN. In IETF117, Cossack from Microsoft present the initial version. And this time we have another co-author added, and he's from working on the multi-cloud integration company. Next page, please. So a little refresh of the background. The scenario is really we have SD-WAN between the CPE branches, and since they have traffic going through the cloud, and some of the cloud traffic will be terminated at the cloud site, and some of the traffic will transit to another CPE branch. So the goal is for the transit traffic, we don't want to do another layer of encryption, decryption, and encryption. So that's the purpose. Next page, please. Here is another scenario when the CPE is at different geographic locations, so that basically hop onto the cloud backbone. Similar goal without cloud gateway to do decryption and encryption. Next page. So the proposal is adding a Geneve header because most of cloud providers are already supporting Geneve encapsulation. With Geneve header, there will be information indicating to the cloud gateway those traffic do not need to be decrypted and need to be forwarded based on instruction, based on the information indicated in the Geneve header. So in the San Francisco IETF, we got lots of comments, specifically from the security area, is mainly about man-in-the-middle attack to the information carried in the Geneve header. So in this edition, we added more on the security part. Next page. So in the security consideration, we added the threat analysis based on 3 different categories. We did a very in-depth analysis. The conclusion is the threat is really causing packet drop. So it's no different than peer-to-peer IPsec. Next page. But for some deployment, some environment, they want to make sure to add the integrity and authentication validation just to make sure those traffic, added metadata is not altered. So based on their proposal, there are a couple ways. One is using authentication. So basically adding a authentication on top, which is simpler than the IPsec ESP. But this method has problem of traversing through nets. So there's some issue with that. Next page. Another simpler approach, depending on deployment, is just do nothing because the user payload is already encrypted. The worst cause of the not do nothing is some packet will be dropped. In some deployment, that can be tolerated. Next page, please. Another way is very lightweight integrity and authentication check. It's almost like adding a digital signature to the actual overhead edit. So here we propose a new HMAC hashing, and then adding the hashing code into like a digital signature to the header as a sub TLE. So we got some preliminary feedback from the security area, and today at the SEC directory launch session, we're going to have another extended discussion on this. Next page. So we think that this draft is ready for working group adoption, and any comments and feedbacks are appreciated. Thank you. No questions?
I'm really happy with the way draft is progressing and your work around different areas of IETF. We will start the preliminary review post IETF, and good work.
Thank you.
Hi, I'm Donald Eastlake with FutureWay. So this is a draft. Ignore the sec dispatch in the draft name. I sort of initially thought it should go there, but this was presented at sec dispatch at IETF 116. And a bunch of ADs were there, and the conclusion was that it probably belongs in routing or transport or internet or security. And there didn't seem to be any consensus, and security didn't seem to be that interested. So speaking with the security ADs, they suggested I should go to routing. Next slide. So this is a fairly general draft. People should look at it to see all the details. I'll just sort of zip through these slides. And the idea is you're adding information to a packet at an ingress and removing it at an egress. So there's additional information as it transits some domain. It could be a sort of limited small domain, or it could be the internet, a large domain. Next slide. Next slide. There. Okay. So this is just what I was saying. And the question is, what sort of things do you need to talk about in terms of security considerations because of this additional information? Next slide. So this information could be information that you only know at the ingress. Things about what actual port the packet arrived on the ingress node, maybe it's a VLAN tag on it, which might be getting stripped if it's being moved to IP, some sort of customer tenant identification. It could be at fine or larger granularity. Or it could be information that you'll be forwarding anyway, but because you're planning to encrypt the packet, you actually also add a plaintext copy earlier in the packet so that it can be accessible during transit, or so that you don't have to look as deeply into the packet to get to it. Next slide. So this additional information can lead to various threats, primarily to privacy. This could be due to surveillance of the links between the nodes, or within a transit or egress node that has been compromised in some way. You don't have a privacy threat presumably at the ingress node because we're talking about information which is all available to the ingress node regardless. And there's also a threat due to possible modification or forgery of packets, either on the link or within a transit or egress node. There are other security threats in general to do with packet deletion or packet replay, but those really don't have anything much to do with the addition of information. And this draft is concerned with the security considerations needed to talk about the threats due to the addition of information to the packet. Next slide. So this exercise has a missing thing. So the example is VXLAN. If you have the inner and outer IP addresses and also the VNI. The VNIs should be listed here and it's missing from this. That sort of thing enables you to fairly precisely identify probably the host or VM, at least the tenant, by observing the packet as it transits through this area or at the egress node. Next slide. So what can you do about that sort of thing? What sort of security considerations are there? And the main ways to address these security threats due to this additional information are minimization, encryption, and obfuscation. And there are also some other considerations related to integrity and authentication and covert channels. Next slide. So there's this dominance relation here. Minimization is by far the best strategy. If you don't put this additional information into the packet, then you don't have any security threats due to it being there. So whenever you can avoid adding additional information, that's the best strategy. Next slide. But if you do have to include this, then encryption is a good thing to consider. Assuming you use good encryption algorithms and have proper key management, then this additional information, which would otherwise have been in plain text, can't be recovered or observed without having that key and knowledge of what algorithm is used. Usually the algorithm isn't secret, it's just the key. So you can do encryption in various ways. You can do link encryption, it's hop by hop, and that protects against observation of the link, but doesn't help at the transit nodes or the egress node. You could do encryption from ingress to egress, and that will help protect it, but that would obscure the fields so that if those fields you're adding might be necessary to determine the routing or the handling of the packet at one of the transit nodes, then that's going to defeat that. So it may not be such a good idea. If you can't encrypt something, then you should consider using authenticated encryption with additional data, where this data you're adding is considered part of the additional data. So it would be authenticated even though not encrypted. But there are some kinds of information about the traffic related to like the number of packets and the size of the packets that it's hard to conceal efficiently. You can add fake packets and you can add padding, and that the more you do that, the better you can conceal this information, but that's not a very efficient thing to do. Next slide. So if all the above fails, it is of some benefit to do some obfuscation. And typically, some security people are very contemptuous, perhaps, of obfuscation. But there are cases where somebody's, I don't know, debugging a network or something, and they look at packets in some way that interprets the fields or shows them as ASCII or whatever, and might just see something on their screen or in their logs that you would prefer they do not trivially get exposed to. So you can do fairly simple things, which fall far short of encryption, but just obfuscate the data a bit, XOR some fixed value with it or so on. And there's also a second dimension, different from that, where if identifiers, packet numbers or ports or whatever that would normally be sequentially allocated, if you do such sequential allocation, you can make it very easy to guess valid values. So there's an RFC on that particular topic, 9416, that you really may wish to assign them in some pseudo-random fashion. Next slide. So you do want to consider integrity and authentication. If this additional information is important to the routing or handling, then you want to be sure that it's authentic. And again, if you're encrypting or using, you should use authenticated encryption, and consider any other fields that you can't encrypt to be authenticated using AEAD. And covert channels are, because you're adding fields, in some cases you're adding a whole new header, like IP and IP or whatever, some sort of tunneling header. There are frequently unused bits or additional fields that are not constrained. So the addition of these fields or additional headers or tunneling headers provides additional opportunity for information to be tucked into the packet and covertly conveyed along the path to something downstream. Next slide. So there's just a bunch of things, SFC has an RFC 9263, defines a whole bunch of additional metadata you can add, exactly the sort of thing, including identity of the types of service you want to provide this client, the client identification fields, input port, and so on and so forth. There's additional fields in the common VXLAN and NVGRE headers. Geneve has very flexible options feature, as does IPv6. At least in principle, you can put lots of stuff certainly into Geneve, which is normally handled in software. Whether your stuff will get through if you add IPv6 options is another question, but there are fields, a place there where you could pack lots of stuff. And even if you just have IP and IP, you get twice as many fields that way, and you may be able to add some additional information here and there. Next slide. So there's a lot more in this draft, and I'm very interested in people to look at it and see what kind of comments they have. And I hope it can be considered for RTWG adoption.
Donald, what is the end goal of this document? Create awareness, make it mandatory to be addressed in some other RFCs. What are you aiming for?
I guess my idea is that this draft would be very useful in that other documents which propose the addition of such fields could reference this in their security considerations section. So that instead of having to go through pages of detailed considerations which are included in this draft, they can effectively include that by reference to make it easier to do other documents.
And that would be a normative reference, not informal.
It would depend a little bit on the details, but commonly it could be.
Then the progress path would be very different. So you really need to consider what you're aiming for here. If it's just for awareness, it can progress informational, and it's really up to you on the amount of information. If you think of making it a normative document, it will need to be in agreement with all the standards you're mentioning here.
Yes. So probably I would be I think it's a way it's currently written, it's a little bit better if it's aimed at informational. But it would still be a useful reference in security consideration section. It just, anyway.
It is. Thank you.
Okay.
And we'll post the list post IETF.
Hello, is the presenter online?
Hi everyone. Can you hear me?
Yeah, we can hear you.
Oh, hi everyone. Today I will introduce the topic of problem statements, use cases, and the requirements of hierarchical SFC with segment routing. Next slide, please.
You have the control.
Okay. Firstly, we permanently introduce the HSFC. HSFC enables an organization to decompose large-scale networks into multiple administration domains. As shown in the figure, we divide the SF2 into a separate domain, or the SF2 may support a different manner of service function chaining from other SF. Then we construct a two-level service function chaining. The first level is SF1, SF2, SF3. And in the SF2 domain, we build the circuit level. That is 2-1, 2-2, 2-3. In this way, it provides better network design, simplified control, and enhance overall efficiency and management. Now, we introduce the use case of HSFC with segment routing. To provide a security service to tenants, network operators have constructed security resource pool in multi-regions. The security resource pool has deployed firewalls, IPS, WAF, and so on, and to provide value-added service to tenants. Well, from the perspective of the overall network, the security resource pool serves as the intermediate node. Then it requires directing tenants' traffic into the pool, which constitutes the first level service chain. And in the resource pool, we need to construct service chains according to each tenant's specific needs, which constitutes the second level service chain. Well, in case where segment routing networks are deployed, the NSH solution may not be the preferred choice. SR-based service chaining is flexible and without altering the underlying network topology, so it is recommended. Here we talk about the problem statements for the use case. The first is dispersion of service resources. It means that the security resource pool is physically deployed in a distributed manner. The second is multi-tenant. The security resource pool provides service for multiple tenants. It needs to provide tenant level service orchestration. Well, the third is multi-vendor. As the security network devices are usually divided by different vendors, they need to be orchestrated by unified external network communication, but not inner. The fourth is dynamic orchestration. In a security resource pool, the SF will change dynamically. The main issue with NSH is that network devices need to maintain the state, such as SPI, SI index table. And when there are changes in the business deployments, all network devices require state updates. So I think SR is more user-friendly. Through the analysis, we conclude 5 requirements for the use case. That is the requirements 1, tenant level service orchestration. 2 meets the needs of different tenants. It requires to support tenant level service chain. And the requirement 2 is tenant information carriage. In order to achieve tenant level service orchestration, it's essential for the packets to carrying tenant information. And the requirement 3 is dynamic allocation of service resources. Due to the dynamic versions of SF in the resource pool, it needs a dynamic allocation of service resource, or we can call it scalability. The requirement 4 is independent resource pool orchestration. Every security resource pool may support different service chains. So it is best to support independent orchestration. They should not bother each other. And the requirement 5 is reliability of service function. It means that when we build an SFC, among the SFC chains, when SF fails, the service chains should be able to bypass that SF. The next step is to refine the draft based on comments and suggestions and seeking solutions. That's all. Thank you.
Greg?
Greg Mirsky, Ericsson. Thank you for interesting presentation. The couple notes I have. You state that segment routing based SFC, you see advantages comparing to NSH. One question I have is, when performing active OAM on SFC, how you envision that packet will traverse? Do you think that the packet will go to service function?
We can allocate a seed for the service function, and the packet just traverses via the seed.
But that would be not a user packet. So basically, it's not the packet that requires their security service. It's a test packet specifically constructed to monitor continuity or measuring performance of service function path. So would you expect that your service function, whatever it's be, understands these specifically constructed test packets?
Well, I will consider it as we can communicate with the email. Thank you.
Okay, another question is that, you use terminology for SFC. Which entity you consider to be a service function forwarder?
Well, the entity may be a device is or a waiter network or a waiter device.
I'm sorry, I didn't get it.
Oh.
Which device, which entity? Because
Such as there or
okay, so I would recommend look at SFC architecture and normalize your terminology with SFC architecture so that the dictionaries are in sync, and then we can continue discussion. Thank you.
Robin.
Thank you.
Greg, could you also send your comment to the list? It was quite long, so the authors can see it. Go ahead.
Jumping from Huawei, quick comments. I think it's better for your requirement. Please take into account OEM. Okay, for the HSFC. Okay.
Thank you.
Okay, thank you.
Hello, good morning, everyone. Can you hear me?
Yes, we can hear you. And
Yeah.
I will pass the control to you.
Thank you. So this is Feng Yang from China Mobile, and we, China Mobile and new H3C colleagues together propose a draft for SRv6 SFC reliability scenarios, and I will make this presentation. So the background is SFC and important application scenarios for SRv6, but there is a lack I think there lack of an overall standard to describe the reliability mechanism. So just Kang just put up some requirement on the reliability. So here I have some proposal on the solutions. In this draft, we mentioned three main network elements about SFC, that is classifier and SFF and also SF, and focus on the link failure between the SF and the SFF, and also the failure of the SF. So we have three mechanisms to cope with those faults. The first one is that is SF due home to the SFF. So in this scenario, when there is a failure between the SF and the primary SFF, we have to direct the traffic to the backup SFF and then processed by the SF. So this scenario is divided into three sub-scenarios. Those are a static proxy, dynamic proxy, and also masquerade proxy. So let's come to the first sub-cases. This case is about the static proxy. So in this case, we consider if suppose there is a failure between the SF and primary SFF. That is the failure between SFF1 and SF. So we have to direct the traffic from the SFF1 to the SFF2. Then the traffic will be handled by the SF. So in this scenario, because it is static mode, SRH and payload mapping relationships are pre-configured. So SFF1 can remove the original SRv6 header and then redirect the traffic to the standby SFF2. There are two options for the redirection. One is to directly change the destination IP. That is simple. The other one is to add an additional IPv6 header with the SRH. So the later way, SF2 needs to remove the outer IPv6 header when it receives this traffic, so that the traffic will be processed by the SF and will not be affected by the failure. So this is a static proxy case. The second one is a dynamic proxy. When there is a failure situation between the SF and primary SF1, we have to direct the traffic to the backup SF2 and then get the traffic be processed normally. Because it is a dynamic proxy, we also need to let SF learn the original SRH. So SF1 will not remove the original SRH header, but by either by modifying the destination address or adding an extra IPv6 header. In the same way, as what in the later case, when SF2 needs to remove the outer IPv6 header when it receives traffic, so that the traffic will be processed by the SF. The third one is masquerading SR proxy. This is similar to the dynamic proxy approach, but the difference is that the standby SF2 additionally needs to update the IPv6 destination address to the last hop of the SRH after it receives that message. So the second topology is that when there is two SF, those are one is primary, one is backup. Those two are each one is connected with each SFF respectively. We consider the failure of the SF or the link between the SF and the SFF. So in case of failure, we have to direct the traffic to the standby SFF and then get those traffic handled by the standby SF. So similarly, this scenario has three subcases. Those are static proxy, dynamic proxy, and masquerade proxy. So the first one is static proxy. In this case, when the primary SF fails, that is SFF1, due to it is a static mode, the mapping relationship between the SRH and the payload is configured beforehand. So the SFF1 can remove the original IPv6 header and then redirect the traffic to the standby SF2, which is this is different with the difference between this case and the dual home case is that the SID of the service function represents the standby SF and the primary SF. Those are different. So there are similarly there are two options for the redirection. One is also just change the destination IP address. and the other one is to add an extra IPv6 header. The rest of the processing is similar with the dual home scenario. The second case is a dynamic proxy. The dynamic proxy is almost the same with dual home cases. That is, we can remove the original SH header, but just have two options. One is change the destination address and add one extra IPv6 header. And the third case, also the masquerading case, which is also similar, but just update the destination address to the last hop of the SRH. So the last one is to consider there are several SFs just connected to the SFF, and there is no backup of the SF. So in case of the failure between the SF and the SFF, and also failure of the SF, the traffic should be protected. And the mechanism is simple: just skip the field SF and let the traffic go. So that which is normally adopted by the industry. For example, when the firewall get overloaded, and the overloaded as firewall will be skipped. That's all of my presentation. So any comments or questions are welcomed, and we're also seeking for feedback by the email or any way. Thank you. Any questions?
Greg.
Greg Mirsky, Ericsson. If you kindly can roll back to dual homing SF case. Yes, thank you. So I have questions. So what mechanism you envision to use to detect the failure?
I think that should be a kind of BFD should be fine.
Okay.
That requires also, sorry.
How you differentiate failure of the path connecting SFF with SF from SF failure?
Actually, we didn't need to differentiate those two cases. We just treat the two cases as similar.
Okay, so because SF failure will probably be equated to double failure of connections from SF1 to SF and SFF2 to SF, and that seems probably will end up with a routing loop.
Yes, that's correct. So in case of the SF1 detect the SF failure, and also in case of the SF2 detect the SF failure, then I think there should be some kind of sync up mechanism to let the two SF get the correct behavior.
Okay, so basically that your schema gets complex and more complex. Okay, thank you.
Thank you.
Dong.
Okay, can you hear me?
Yeah.
Yeah, thank you for your presentation. Actually appreciated that ideas. And here I only got a tiny comment about it. So with my understanding that there's two methods of SFT protection, which is SF protection and SFF protection. So I'm wondering that if there is a possibility to combine the two methods together to form a global vision of SFT protection. Thus, the SFF and SF here maybe form a spine architecture. So is there any possibility or is there any thoughts about it?
Yeah, that's a good idea. So actually, this is the one we should consider in later.
Okay, thanks.
Thank you.
Yeah, somehow we cannot take back control of the slides. Feng Yang, can you please close your slides? Oh, I think I can do that here. It's not working.
Tech support. Did you do it? Problem solved.
You want to control yourself or?
Yeah.
Okay.
Just ask for it.
You should be logged in.
I'm logged in. What's for control? Is that correct? Okay. Yeah. Hello. My name is Roland. I'm presenting Kira, which is basically a scalable zero-touch routing designed for control planes. The goal was to provide a resilient control plane, especially the connectivity for the control plane. So all the fancy things that we want to do with networks, like doing SDN, NFV, what have you, also AI stuff or intent-based network management that requires solid foundation with respect to connectivity. So you don't want to lose the control of your network. Especially, it's also important to avoid any circular dependencies while you control the network. And we wanted to support in-band, out-of-band, or hybrid control. And so the goal is to more or less guarantee the controllability of every network device. We found that the existing solutions are either not scalable, are not zero touch, or are topology specific, like Rift, for example. And Kira could be, for example, an alternative routing protocol for the NMS ACP, the autonomous control plane, offering certain advantages over the current envisioned Ripple ACP. So I said it's scalable, so it is able to connect thousands of devices in a flat manner, so to say, because it's ID based. So we don't require any hierarchy or aggregation. We do not use locators, so there's also no ID locator mapping. But we have a trade-off, which is stretch. So some routes are longer than shortest path routes, but it's also tunable. We always have shortest path to the contexts that are in the routing table of a node. So you can actually, as a controller, for example, you're still able to efficiently control your resources. It is zero touch, which means it doesn't require any configuration, and it is self-organizing, so it adapts to whatever topology changes and also while the network evolves. It uses self-assigned addresses for that purpose and has no other dependencies. So what it provides is basically a resilient control plane connectivity based on IPv6, because we want to embed the IDs into the IPv6 addresses. And yeah, it is loop-free even during convergence because we're using source routing and path-oriented routing.
We found that it works well in and across various topologies, be it sparse or dense, like in data centers. And it's, as I said, just it's not hop by hop forwarding, it's path-based forwarding, so you can do any kind of tricks like multipath routing or traffic engineering if you want to. This is a rough overview of the architecture. So basically we have a routing tier with the routing protocol, and we have a forwarding tier. So the routing protocol, as I just said, uses source routing for its own messages, while we want to have a more efficient forwarding for the control plane packets, and that's why we are using path ID based forwarding in the forwarding tier. So the control plane applications simply use a normal transport over IPv6, so they don't need any special adaptation. And so what we also can do is like supporting certain services like topology discovery in a very efficient manner. Then you can do whatever service placement or other network management stuff, but when after discovering the topology, and we have a distributed hash table on board, so you can have simple name and service registration lookup or discovery schemes, which the control applications can then use. Yeah, so there are some further features. Last year I presented how it works, and this time I'm presenting a little bit more about its use cases and features. This year we also introduced a concept like domain scopes, so you can have a global scope, you can have organizational scopes, topological scopes, but the nodes still keep their node ID. So you have the same node ID in different scopes. And so while let's say in the global scope, you cannot avoid that you route via some other nodes. Here you can then constrain your routes to stay in a certain domain, like here in this example, the path should stay inside the domain J here. We also support end systems in the sense that end systems do not route, and then you can have a little bit more lightweight approach, so you don't need to send route updates and so on. What is currently ongoing is security measures, so we're working on that. It's not yet finished. So I submitted a first draft, which is not yet complete, but an update will follow soon. We have running code, so we tested the scalability using a simulator for the large-scale simulations with hundreds of thousands of nodes. We have an early, or had an early prototype, SDN-based, which uses the Open vSwitch in the forwarding tier. Right now, we are having a first implementation in Rust, being a native Linux routing daemon. The forwarding tier then uses NF tables. And basically why I'm here, we want to standardize it and we want the IETF expertise. So the question is whether we continue at working group draft, whether there's enough interest to even form a working group on that. And I also set up a side meeting or Barboff tomorrow. So if you're interested, please join. I will a little bit explain more about the use cases. Any questions you have, we can discuss on collaboration and also on next steps towards standardization. Thanks.
Anton?
Tony P. Juniper, just one clarification question. So I understand correctly, this needs a new data plane, right? So the forwarding is its own path, right? It's not just IP forwarding, it's a new data plane.
You can use existing data plane mechanisms to forward. So, I mean, you're usually using it to forward the control plane packets, right? Not the data packets.
So whatever. The data plane is a new data plane. Okay, thanks.
Anton?
Yeah.
I think I'm going to ask similar question as Julius. How Kera is different from Babel? What is the difference with Babel protocol?
I didn't get that. Sorry, different from what?
Babel,
The
it's a
protocol? Babel.
Babel. Okay. Yeah, it's as I said. I mean, it's first it's ID based, so it doesn't use any topological addresses. Then it's scalable in the sense that you can have 100,000 of nodes, and it's designed mainly for the control planes. So and also it doesn't guarantee any shortest routes, shortest path routes. So for some destinations, you have longer routes than shortest path. I guess there will be another question with respect to that.
So Julius Krabachek. No, actually, I was going to say something different, but thank you very much, Antoine. So there is a community that has years, decades of experience with self-organizing networks. It's the ad hoc networking community. Okay, there is an IETF working group, that's MANE, which is meeting today at 17. And I think it might be a good idea to come to meet the ad hoc networking community and to see whether well, how your technology compares to the self-organizing technologies. And here I don't want to set a trap for you. I think so the ad hoc networking community has experimented with DHT-based routing some 10 years ago.
Yes.
And the results were not very good because of the problem that you have given, is that distributed hash tables tend to lead to essentially random routing. So you end up going around your network rather than doing shortest path networking. But I think it could be an interesting exchange. We're meeting today at 17.
Yeah, okay, thanks for the suggestion. So Kira was not explicitly designed to be used in the ad hoc environments, but it probably could be used. And yeah, I'm well aware of that prior work. Yeah, thanks.
So I think I would support Julius' comment. Please go to MANE and see whether there's any work that could be done together. So you referred to FIP presentation a year ago. It's behind the paywall, so people cannot actually see what's in there. So you either should provide more content within the draft, but it's unreadable, right? The presentation in FIP.
Presentation in what? Sorry.
What was it? You presented the event. I remember reading it before, but I have access to it. Most people don't.
Okay.
So thanks for the presentation.
Hello, everyone. This is Daniel Huang from ZT. On behalf of authors, I will present service ID for address and networking. Please, next slide. Actually, we are, no, go back one slide. Okay. We have been reminded in the mailing list the service identification is cliche, and this will be the eighth one. So I understand the community worries about the terminology, but actually we are quite open for the terminology. Maybe we will actually we're working on it with the more specific one. And anyway, when it comes to the service ID of this draft, service ID is designed to be an entity which refers to user-warranted services or the networking and computing capabilities as service, which is indicate to the users to either explicitly or implicitly. Actually, the service ID in this draft we mean is explicit way. And when it comes to the benefits of why service ID employment in the routing network is we can identify a service with disparate requirements when we treat the traffic accordingly,
and also a lightweight interface to users rather than only to the operators, which is the way for the existing mechanisms. And also the service ID right here in this draft is designed to be relevant to across the terminal, network, and cloud. And when it comes to the existing practice in routing network, actually we have both implicit and explicit way, such as mapping with 5 tuples. And we also have a couple of very interesting and impressive drafts in routing community, which is service address of ROSA and the APP ID of APN computing service ID of CATS. Next slide, please. So right here, I will identify 2 use cases which appears new to the community. The first one is service mesh across multi-clouds. When it comes to multi-clouds interconnection between the microservices, there will be multiple layer 7 proxy traffic to be intercepted in the networking. So quite overwhelmed, the performance price will be involved in terms of delay and complexity. Also, the API gateways that the DCs could be under operation of different parties, which have quite different interfaces to outside parties. So additional complexity incurs for microservice access, please. And the second use case is multi-cloud and domain interconnection. Also, under this scenario, there will be quite different underlying technologies involved. Well, when it comes to end-to-end the service traffic forwarding, actually the service requirements needs to be consistently guaranteed. So currently we do not have a unified mechanism to ensure the end-to-end requirements to satisfaction. And also additional delay cost occurs when the gateways of different domain handles the tunnel operation, which involves the encapsulation, decapsulation. Next slide, please. So the gaps of the existing service ID mechanisms in routing network, the first one is state burden. Mapping state would increase exponentially while the service migrates from the traditional centralized cloud to edge sites. And as far as the granularity and TE, the 5 tuples could not identify the subflow of service, which could be far more networking sensitive than the rest, such as video service. And the bind seed and color and DSCP based TE could not reflect the service in a fine-grained and explicit way. Actually, it's restricted in a particular networking domain. And also, the existing service identification is operator-oriented rather than user-oriented. And 5 tuples will be always be terminated by the cloud gateways such as NAT. Well, actually, the more benefits, the more sophisticated convergence to the networking community could be made when the identification could further reach out into the cloud. Therefore, layer 7 gateway routing and forwarding will be terminated with quite significant performance prices. Next slide, please. Okay, we'll try. This is requirements. Actually, when I talk about use cases and gaps, I actually indicate the major requirements. So I will not read one by one. Next slide, please. This is actually a diagram to indicate how the service routing are to be managed and governed. Those actually service ID is governed and managed by a control system. And also from a provider and user's perspective, service ID is an agreement and explains the interface between the provider and the user. Next slide, please. The instantiation of service ID. Actually, the service ID could be in IPv6 header and IPv6 extension header, which will incur quite different workflows. But this draft will not focus on specific solutions. We will focus on use case requirements. Next slide, please. Because service ID, which is relevant to cross-terminal networking cloud, is employed. So a hierarchical OEM mechanism could be enabled under the system. And next slide, please. The draft focuses on rationale of standalone service ID in routing network rather than a specific framework solution in the current stage. So the use case system and the gap analysis will be refined and decoupled from this draft. Any comments, suggestions?
Okay, this is Fang Gao from the Zhongguan Laboratory in Beijing. Could you go back to the slide 7? Yeah. I think the definition of the format is clearly, but I have some comments about the practical implementation. The first is about the one who publish and subscribe the service ID. Is the end user on the left side or some application of the tenant who called API gateway or use the macro service on the right side in the cloud or in the data center resource? This is the first one. And the second question is about the control system. As you mentioned in the previous slide, it will be relevant to the terminal network and the cloud. And the control system here is the one for the network or the one for the cloud. I think normally they cannot have the unified control plane system. And the third one is about, you mentioned the situation. The target use case is about the multi-cloud and the control plane between which cloud, whether it needs some synchronization between them and how. And then we go to the cloud system inside. And we know normally the service gateway of all cloud is normally be controlled by some component named Newton or something like this. But I think here the service ID is defined in some code of the tenant. And is there some agreement or some synchronization between them? I think it's better to make it clearly in your document or somewhere.
Okay, thanks very much for your questions. I will try to answer on the one, but actually the service ID under this diagram is instantiation, which is not a solution. And what we want to indicate in this slide is the service ID will be controlled and governed by centralized system rather than initiated from the terminal independent or some networking devices integrated. So the network could operate the service ID from the perspective of the end-to-end delivery.
We'll try to take a few more questions. So you've had quite a number of questions. If you send them to the list, I think it would be much more productive to discuss it there.
Thank you.
I'll talk to you offline.
Xu from Huawei, just a very quick clarification question. You have mentioned in the previous slides about reference to the existing technologies like ROSA, but still I think it is a little confused to me. What is the relationship between this service ID and the previous solutions, for example, APN? I think more clarifications will be necessary here.
Okay. Because of the time, actually, originally I applied for 15 minutes, so I simplified the statement about the difference between the service ID of this draft and the APN ID and the service address of ROSA is, I believe the service ID in this draft is
is unique across the terminal and networking and networking and cloud, and it's a quite lightweight labor rather than the profile, particularly in the forwarding plane. I believe that's the major difference between the service ID, this draft, anyways, this APN ID, particularly the APN ID will be, from my understanding, issued from the ingress load, and which has only the semantics within a particular limited networking domain.
Linda, please ask the question. Donald, we close the queue after Linda. Sorry, please send it to the list.
Am I in or out?
Linda, if you have a quick question, ask.
Okay, I have a very quick question. So the service ID, is that the IP address, or is something embedded inside, like a extension header or flow label?
No, it's not a service. It's not an IP address. It's the standalone identification. But it could be instantiated in something like the destination address, IP address. But it's not IP address.
So is that service ID in the payload, in the packet?
Yes.
Oh, so you are adding another ID in the packet,
Yes.
just like a flow ID is,
Yes.
right? So why can't you use the flow ID then?
Yeah. Yes. Actually, in the about the encapsulation solutions, the slide, number 2, I believe that's a, but I do not make more specific explanation for the solution. Because they drafted now, I do not want to focus on the specific solutions, and I want to identify the gaps and requirements. Thank you.
Donald, we're out of time. Please take it to the list. Apologies.
Take 2 seconds.
Shushan.
Yeah, just a quick response to the previous feedback. I think the assumption from APN that is inside limiting domain is based on some consensus of the community discussion, but that is not a limitation of the APN technologies itself. And today we will give some presentations about the end-to-end application aware networking. So maybe we can discuss more about this point.
Yeah. Actually, I read the drafts. I believe it's impressive and interesting.
Yeah.
Yes. Okay.
Great.
Thank you.
Yes, thank you. Thank you.
Hello, good morning. This is Wei Chang from China Mobile, and I will give some overview on the consideration on the reliability in AI data center networks. So next page. Okay, as you know, if you want to training something like a ChatGPT, you may need several thousand GPUs. So the big cluster you should build. Let's take a view of the AI training network. So basically, it's very large scale, even more than a big city metro network. And the bandwidth is really high. You may need to use such as 400 gig Ethernet, even 800 gig Ethernet. And the training duration is very long. It will take several days, even several months. So in this condition, the network is really important. Here we have some statistics about the hardware failure. So you know, if you have a 8,000 GPU cluster, the possibility of experience GPU card failure during 1 month, it will about 99%. That means definitely it will have at least one GPU card failure. Let's take another example, such as the optical module failure. For the big data center, you will have more than 100,000 optical modules. So on average, one optical module failure occurs even 4 days. So that means the network failure will be important factors when we build the data center network, especially for AI training. So next page. So here we list some existing mechanism for the reliability in the data center network, such as faster failure detection, the local faster failure, switch over, the failure notification, the global faster failure over. When you look at the convergence time, those kind of a mechanism takes several milliseconds to even several seconds. It's too long. So for AI training, some experience shows that if more than millisecond failure over, it will cause the training grasp, or you should go back to the previous checkpoint. So it will reduce the it will have the big impact on the training efficiency. Here there is two example. One is for the local failure. The local failure, if you use the current mechanism, you need tens of milliseconds to get a switch over. And for the remote failure, and you even need to take several seconds to get the recover. So it's too long to meet the AI training requirements.
You're on third slide and half time.
Yeah, okay. Next page. Okay, because we have mentioned the local fault. So here gives some detailed and you need to take about tens milliseconds to get the local fault recover. Next page. And you need several seconds to get the remote fault recover. Next page. And for the Dragonfly topology, and if you have the intra-group fault, and the fault detect and the failover will take tens milliseconds. Next page. And for the intergroup fault in Dragonfly topology, it will take even 10 seconds to get switch over. Next page. So currently, no matter for the fat tree topology or the Dragonfly topology, the current fault detection, the local failover, the notification, and the global failover seems not good to the AI training. Next page. So I think if possible, we can have some new mechanism, especially for the AI training network, such as for the fault detection mechanism, we can shorter the duration within sub-millisecond. For the switch over, we can narrow that under a sub-millisecond. Even we can have some new notification mechanism. Then totally, if we can control the switch over time within millisecond, maybe 100 microsecond, we will dramatically improve the AI training efficiency. I think it's possible because the AI training network topology is very simple. No matter the fat tree or the dragonfly, it's fixed. So the other factor is that the AI training network within a limited location. So all those things is totally different from such as a mesh network or backbone. But currently, the mechanism for the switch over designed, dedicated for the one network. So it's possible for us to develop some new solutions to meet the AI network. So we also would like to call for attention for those requirements. It's maybe a new opportunity to do something here in the future. Next page. Okay, that's all. Any question or comments? Thank you.
I'll start as a working group chair. So is your goal here to call, practically you're asking to move notification from control plane to data plane, right? That's the only way to go into single digit millisecond notification. Is your goal to propose fast notification in data plane, or you're just calling for a solution?
So I think now this draft, we just give some problem analysis. We did not give any possible way to solve that. From my point of view, we should do something in both data plane and the control plane. Maybe some new thing should be raised. Yeah.
So I would advise to look about 10 years back. There are a number of solutions with regards to fast notification, how it can be implemented data plane. Just take a look and see whether it addresses your requirements.
Okay, thank you.
And another point, you are mentioning some minimum time between failures, some numbers. If you could provide some reference how they have been computed, it would be very useful.
Okay, thank you.
Julius.
So you probably said it, Julius Krabacek, sorry.
Well, that's the mic, please.
You probably did say it, and I may have missed it, but why do you need sub-millisecond? I find it very exciting that you need sub-millisecond convergence times, but why do you need sub-milliseconds? What's the reason for that?
Yeah, it's a good question. In fact, we have some experience. We also are working together with some our partners. So that is experience. If you can control the switch over time within 100 microseconds, then you will have some way to keep the training ongoing. Instead of you should go back to some checkpoint or even restart the training. So why it is because when you running the training and you may have some uplier requirements for the network, such as RDMA or some collective communication models. So it's different from the different models. But if you can limit the convergence time, it will greatly improve the training efficiency.
Okay, I'd really like to understand that, but I guess we need to take it offline. Right?
Please take it to the list. And today, 5 to 7, we are going to have side meeting in context of routing working group, we'll specifically talk about some of the topics and cost of packet drop really in AI networks. Victor, be quick, please.
I'll be really quick. I think this echoes what you said, Jeff. I'd be really interested to Victor coursing. I'd be interested where you got your data on failures, because what you presented there doesn't really match what I see in production. So I'd like to see how you computated those failure rates and how you saw that data set would be interesting for us to look at.
So the time is limited. Yes, maybe we can talk about it when the side meeting. Yeah, it's a good question.
But ideally, I would like you to have reference in the draft how you've computed your minimum time between failures and repairs and all the metrics. Because operationally, I have very different data too.
Okay, thank you.
Quick question, please.
Yeah, quick question. You mentioned in your requirement the topology awareness, right? You mentioned the fat tree and dragonfly for the AI fabric or AI networking. I wonder if you are going to design different mechanisms for different topologies, or you want to have a general mechanism for them?
Maybe generate the common solution is good. So I don't think we need to develop the different solutions for different topology, but we really need a new one. Yeah.
Okay, thanks.
Okay. Thank you.
Thank you.
Okay, I'll try. My name is Lily Liu. I'm from Huawei. My presentation is also about the AI training, the data center network. The topic is coordinated congestion management. Please go to the next slide. So the previous presentation has already introduced some background of AI training, but let me talk a bit more on that. So we know the large-scale AI models have a huge number of parameters. So it is imperative to run this distributed parallel training on thousands or even more, tens of thousands of GPUs to train the model. This figure is a simplified illustration of how the AI training works. You can see that the training is repetitive, iterational iteration. And in each iteration, it has, generally speaking, it has the forward computation and backward computation. The communication is always there. Our target is the communication is used to synchronize the gradients among different GPUs and push the AI training going forward. And our target is to reduce this communication time in order to increase the GPU utilization, because GPU is the most expensive resource in AI training. Then looking at the communication characteristics, this table shows some characteristics of different types of parallelism which are used in AI training. Generally speaking, it has a large requirement of the bandwidth of the internodes communication. It can be several gigabytes for different types of the parallelisms. Such communication is quite different from what we have today in traditional data center. It requires large bandwidth. It shows many bursts. It does not have many flows at the same time, but the flow size is big. So please go to the next slide. So we say that the AI fabric is the GPU to GPU interconnects for AI training. It needs the congestion management. Why we say so? As mentioned, the shortening communication time is key to the AI fabric. The most strict way we can think about is to increase the bandwidth, right? But what I want to emphasize here is the network bandwidth should be the effective network bandwidth. What does that mean? Assuming we have 800 gigabps Ethernet for AI fabric, but if several links are very busy and other links are free, the effective network bandwidth is low. Or if the packet loss leading to many retransmission, the effective network bandwidth is also low. So what I want to say here is we should try to fully utilize the network bandwidth and increase the throughput so that we can increase the computation efficiency. Therefore, the congestion management is a must. The congestion management includes the congestion control and load balancing. For load balancing, traditional way is to use the ECMP in data center, but it does not work for AI fabric because it is easily to hash the elephant flows to the same path. Then adapter routing turns to be a new choice. Adaptive routing dynamically shift the traffic path of flow based on network status. Actually, in previous IETF meeting 116 and 117, there was a presentation about Dragonfly Plus topology. In that presentation, it also mentioned about adaptive routing. And at that presentation, at the end of that, it raised several questions, open questions. The first of them is regarding the adaptive routing and congestion control. It asks, how to decide what to do, the shift flow or adjust the congestion control? That is a good question. Although it is raised towards the topology of Dragonfly, but I think it is valid for other topologies like fat share clause, which are also used in AI Fabric. Um, Currently, the adaptive routing and congestion control, they work independently. They do not have coordination. That will bring some problems to the AI Fabric. Please, next slide. Then before I talk about the issues, first let's look at different types of congestion. The fan-in congestion, it happens in overscribed topology, like the ingress traffic is bigger than egress traffic, or the traffic sent from the high-speed port to low-speed port. Then the second is the in-network congestion. It is usually caused by improper load balancing and which may overscribe the egress ports. The last, the in-cast congestion, is very famous. Multiple senders transmit data same times at the same receiver. In order to explain the following content, I categorize the in-network congestion as the type 1 congestion, the other two as type 2 congestion. So now we can talk about issue. If we have the type 1 congestion, it is very possible both the adaptive routing and congestion control are activated. The adaptive routing will shift the flow to another light loaded path. Meanwhile, the congestion control may set the ECM bit, if it is DCQCM, set ECM bit to reduce the flow rate. As a result, this flow will run on a light loaded path with a low rate, at least for a while. This definitely reduces the effective network bandwidth, right? Another case, this time is type 2 congestion. For the type 2 congestion, the only way to mitigate is to reduce the sending rate. That means to perform the congestion control. Any additional adaptive routing on this flow will not only fail to mitigate the congestion, but may also introduce the unnecessary out-of-order traffic. So the uncoordinated adaptive routing and congestion control may deteriorate the system's performance. Please, next slide. So here's our proposal. The basic idea is to distinguish the CC traffic and non-CC traffic and treat them differently while the congestion happens. A CC traffic that refers to the packets in the flows which cause type 2 congestion, and non-CC traffic means the traffic which cause type 1 congestion. For CC traffic, we just perform the congestion control and do not perform adaptive routing. But for non-CC traffic, we first consider to perform adaptive routing. Only if the adaptive routing are not available, then we change to perform the congestion control. Next slide. I'd like to give you an example to illustrate how the scheme works, but before that, let me explain two important components in this scheme. First is the tag, the coordination tag that is inserted into the data packet. It has two parts, CC indicator and AR indicator. CC indicator indicates if the packet belongs to a flow which needs congestion control. The default value is 0. Then AR indicator, it indicates the location of upstream point where adaptive routing can be performed. Usually the switch just checks the local passes to see if there is any available paths to shift the flow. Sometimes it is possible that it cannot find available local passes, but there is upstream point. It could be a switch or could be host. That point can find another path for this flow to bypass this switch. The AR indicator just points to the location. Next slide. Another component is the notification message. There are several types, the CC notification and CC release notification. They are used to set or unset the CC indicator at the source site. It is sent from the congestion point to the source host when the type 2 congestion is detected. Like, for example, if it is the congestion happens on the last hop and on the egress port, this is detected as the incast traffic, that is type 2 congestion. the upstream, another type is the upstream AI notification. This is used to notify the upstream point to perform adaptive routing. Please go to the next slide. Let me give you example. Perhaps that helps to explain the scheme. This is the four-layered fat tree topology. You can see that the layer 1 and layer 2 switches, and together with the host, are located in the computing racks. Layer 3 and layer 4 switches are in the switching racks. At point 1 in this figure, the host sends a packet. It sets the CC indicator in the data packet to be 0. That means this is non-CC traffic. When this packet arrives at the layer 1 switch, this is point 2 in this figure. The layer 1 checks there are multiple passes for forwarding this packet. It just chooses one of them according to its own strategy and updates the AR indicator to be layer 1. That means I am capable to perform adaptive routing. Then at point 3 in this figure, the same situation, the layer 2 updates in AR indicator as layer 2. Then at point 4, congestion happens there because this is in-network congestion and the CC indicator of the data packet is 0. So layer 4 decides to perform adaptive routing. Unfortunately, it cannot find proper light loaded paths, but by reading the AR indicator in the data packet, it knows upstream point layer 2 can perform the adaptive routing. So it generates an AR notification and sends it back to layer 2. After receiving this AR notification that is at point 5, the layer 2 chooses another path for the subsequent packets of this flow. It is shown by the new path. It's shown by this red line in this figure, and you can see the red line just bypass the congestion point. Then at point 6, there is incast congestion. So a CC notification is sent to the host. So finally, at point 7, the host sets the CC indicator of the subsequent packets of this flow to be 1. So those packets will not be performed adaptive routing when they traverse the network. Well, my last slide is next step. So I've already uploaded the draft. I encourage discussion on the mailing list and welcome your contributions. Thanks.
Before we take question, a couple of comments to your presentation. So you assume there are flows in most adaptive routing solutions. There are no flows, there are packets.
Sorry.
You assume there are flows. There are actually no flows.
There are flows.
No, there aren't.
So,
We discussed another
okay.
time.
Sorry.
Second feedback is that whether you can load balance traffic or not is often depends on RDMA semantics or DMA operations.
Maybe
So,
we can
yeah,
discuss
so
offline.
many assumptions in the draft are either incorrect or missing.
Yes, because I have limited time, so we can have more discussion offline.
Sure. Thank you. Thank you.
Okay, thanks for your presentation, and I appreciate the idea of the classification of congestion control types. Well, it reminds me of InfiniBand, so there are two comments. Well, the first one is the congestion types classification. Is there any connections with the root and victim scheme in InfiniBand, and should we inherit some ideas from that? And the second comment is that's, well, in HPC we use RDMA, and for L4, layer 4, we have some FECN and BECN bits for congestion notification. So is there any connection between an IP layer ECN and the level 4 congestion control? And that's my question. Thank you.
Yes, there are different mechanisms for congestion control, and I think in InfiniBand it also has the different strategies. But I think here the key point is we need to coordinate adaptive routing and congestion control. It does not, we do not intend to invent some new schemes for the congestion control or adaptive routing, just to see they can work together.
Okay, thanks.
Okay, then the Dunbar, actually I'm following the similar question earlier. there's ECN like IFC 6040 being already documented on the congestion control. Would you be able to analyze that and see if that approach can be applied to your work?
ECN is not, it just has one bit used in congestion control right now, right? So we could reuse the ECN. We actually, here is the coordination between adaptive routing and congestion control. We can still use the one bit ECN like DCQCN uses that. We can still use that mechanism for congestion control, but we just to say when we need to trigger the congestion control or when we need to perform adaptive routing, but you can still use the ECN if we decide this is opportunity to trigger the congestion control.
Thank you.
And so today, 5 to 7, we are going to have again side meeting dedicated to networking AI clusters. We'll have Google presenting CSIG, which is a signaling mechanism that could be used and actually used for congestion control. With regards to using more data to signal congestion, there's an ongoing work in congestion control working group under HPCC that uses in-band telemetry to provide much more high fidelity data to the sender to throttle or rebalance. And we are exactly on time.
So for the side meeting for TLFA, it's gonna be tomorrow evening, 5 to 6 o'clock. So I already sent an announcement to the list. If you are interested, please be there.
And thanks everyone, and we'll see you in Australia, hopefully. Have a good week.